good morning, or whatever time it is where you are. I hope you're well. Here we're looking at e to the x. You might have seen this function a little bit already. If you've studied AS level, you'll have encountered it in the Poisson distribution. You might have also used it within the logarithms work that you did at AS level. You may not have seen the formula for e to the x before, so I'll try and break it down. We've got it up here. We've got increasing powers of x. So we've got, well, x to the 0 effectively here, x to the 1, x to the 2, x to the 3, x to the 4. And then we've got increasing factorials along the bottom of these fractions as well. So we haven't written these in here, 0 factorial and 1 factorial. Those are both equal to 1. So you're dividing by 1, it doesn't matter. 2 factorial, 3 factorial, 4 factorial, and so on. This is an infinite series. So the dot, dot, dot indicates here that there are extra terms. We're just not going to write them all because that would take an infinite amount of time. The factorial symbol tells us that we should multiply by every single integer down to 1. So for example, 4 factorial, the formula for that would be 4 times 3 times 2 times 1. And we can work that out as 24. Now, we will be looking at differentiating e to the x. To make that a little bit easier, I'm going to rewrite the factorial terms in an expanded form. So I ended up typing it because it looked a lot neater. Let's differentiate this expression. And let's see what we get. So we're just going to differentiate every single term individually to see what happens. Now, differentiating constants always result in terms disappearing, going to 0. So differentiating this first term, differentiating the 1, will just result in a 0. Differentiating x will give us 1. Now this term, there's a little bit more going on. I won't simplify the full fraction yet, but if I do take the power down, I'm going to get 2x over 2 times 1. Here, I'm going to get 3x squared over 3 times 2 times 1. And here I'm going to get 4x cubed over 4 times 3 times 2 times 1. Now the reason I've written out these factorials fully, you might be able to see that there's going to be some terms cancelling out in this expression. So the 2 that has been generated from differentiating is going to cancel out with the 2 here. The 3 and the 4 are also going to cancel out. So when I tidy it up, I get this expression. I can ignore the 0. I've got here x over 1, x squared over 2 times 1, x cubed over 3 times 2 times 1. And you can rewrite those in factorials. I'll just ignore the x, the 1. Oh, not enough room there. Let's write that again. X squared over 2 factorial, x cubed over 3 factorial. So when we differentiate e to the x, we end up with a very familiar expression. The x squared over 2 factorial term differentiated to x. The x cubed over 3 factorial term eventually differentiated to x squared over 2 factorial. And this term, with the x to the 4, differentiated to x to the 3 over 3 factorial. So you get this cycle where each term differentiates to the term just before it. Because e to the x is an infinite series, you will get some terms over here that do in fact differentiate to x to the 4 over 4 factorial. So the key here is that differentiating e to the x just gives us the exact same expression. Again, the differential of e to the x is e to the x. So it turns out that e to the x is the only function with this property that it differentiates to itself. And that's quite a powerful property that sees it crop up in many different areas of maths.